Work it, make it, do it, make sense.
Right, come on people, don't be shy. There's room in the middle. If anyone saw Catherine's Ignite talk last night, it's all about hug your fellow developer. So do move into the middle seats there, people. Don't be shy. I have a few more minutes to go. I hope everyone's enjoying DevOps UK so far. I actually helped start the very first one 5 years ago, and it was myself and a bunch of London Java user group members who ran the first DevOps UK. We had no idea what we were doing. It was absolutely manic chaos. Putting on a conference like this is incredibly difficult. So the following year we asked Mark Hazel to take over as quickly as he could, and he's done, I think, an amazing job. And this year has been the biggest show yet, and it's fantastic to see. So today I am going to talk about performance tuning. And the thing I'm really going to get across to you is the methodology of how you go about doing this. Right? So when you get the call at 3 o'clock in the morning, who here's had a call at 3 o'clock in the morning? Ooh, quite a few of you, right? And your users or your manager are screaming down on the phone at you. The e-commerce website is down. We are losing millions of pounds or millions of euros per minute. The world is ending. It's all over. And you have no idea where to begin. Right? It could be the fact that the end user has simply cut their internet connection off. Right? It could be your data center is currently on fire. Who knows? So the one thing I want you to try and take away from today, there's going to be some technical slides and quite a bit of detail, but the one thing you really want to take away is the methodology, and I'll reiterate on that point. So this is me. I'm the Diabolical Developer. Some of you may have seen me speak before. I'm currently the CEO, I was demoted from CTO, of a company called jClarity. We use machine learning to do performance tuning. It's really good fun. What you do is you hire a couple of PhDs, you let them do some machine learning stuff for about 2 years, you pray they will get a result, and you try and build a product company out of it. I recommend it if you're a risk-taking person. So, what is performance anyway? Performance is really about the efficiency of something, of how something reacts, or how something fulfills its purpose. So, are you getting the 100,000 transactions per second? Are you getting the response times of the login page responds in 1 second, or are you not? It's also got a lot to do with how much resource you need to process this work, right? Performance tuning is actually almost a branch of economics. You have a certain amount of set resources, certain amount of set hardware, certain amount of threads, CPU power, RAM, so on and so forth. How efficiently can you make all of that work for you? One of the interesting fallacies I used to see a lot of is that when people see a fully utilized or close to fully utilized CPU, they think that machine is performing badly. And I'm like, no, this is good. The CPU is one of the most expensive pieces of hardware you can buy on the planet today. You should be using that darn thing, right? If you're using it at 80% and you're still meeting your performance time goals, then that's great. You're actually utilizing your hardware really well. User requirements are very, very important. And you don't want your users just telling you, I want the website to be fast. You actually need to have a statistical curve of what the throughput goals are, latency goals are, and what the resource goals are as well. Because you don't have unlimited budget, right? You're not Netflix, you're not Amazon, you can't just go out and say, well, let's go provision 10,000 machines. Okay, your managers or your chief financial officer will be giving you a budget. So I'm going to cover 8 things. I'm going to go pretty rapid fire through some of these. But the first 4 sections are the bits you really want to concentrate on, right? The following 4 sections after that sort of point in time how we do performance tuning today, given the technology we have today, but that changes really rapidly. And my one piece of advice is do not performance tune from Stack Overflow. It's a really, really, really bad idea. So the last 4 sections, treat it like Stack Overflow. There's some reasonable advice in there for today, but it does not apply specifically to your hardware, your application, so on and so forth. First 4 sections, the methodology stuff is what you want to concentrate on. So, it is all about resources. So I'm going to do a quick poll. How many of you actually know what your production servers are in terms of their hardware configuration? So a paltry sum of about 10%. Shame on the rest of you. You need to go out and talk to your hardware people, your system administrators, get out your hardware manuals and actually understand what it is your software is running on, both from a hardware level, an operating system level, a virtual machine level, since virtualization is all the cool rage these days. And who here is using Docker or a container? Quite a lot of you. Wow. Okay, so all of you also need to then therefore understand how the Docker container stuff's been configured. Virtualization is making it worse for everyone. When you think about it, your code is now running on a Java virtual machine, which is running on a Docker container, which is probably running on a virtualized operating system, which is then running on a real operating system, which is then finally, maybe if you're lucky, running on some bare metal somewhere. It's not good. And every one of those layers takes a hit. Talk a little bit about cloud. Who here is now hosting on cloud? Cloud. Oh, actually not that many of you. We shifted from an on-data center-based application to cloud. We're a software as a service, so we're a multi-cloud software as a service. We have 4 different cloud providers providing our stuff around the world. Cloud is horrible for performance. It is absolutely terrible. We are lucky if we get 2 nines worth of uptime from our cloud data centers. We're on the open internet, so the data streaming between our data centers goes out into whatever the open internet is, which is controlled by God knows who. If, for example, we're running on a bunch of Amazon nodes which happen to be too close to Netflix on Christmas Eve, our network is just utterly destroyed because a whole bunch of toddlers are out there watching Santa's Christmas 2, Revenge of the Elves. It's not good. So when you're in your own data center, you have massive amounts of control over your hardware, your network, and all these things. So you can get quite reliable performance. But when you shift to the cloud, even as application developers, you really have to think very, very differently. You have to start thinking about your fault tolerance, your resiliency, what happens when things time out, what happens now that all of a sudden all of our transactions are an order of magnitude slower because that database transaction is going across the open internet, so on and so forth. So you really have to think quite differently. Uptime is rubbish, as I mentioned before. People always talk about, but you can just spin up another 10 or 15 servers. When I do a demo for my customers and I spin up my 20 Amazon AWS nodes to give my demo, I have to do this an hour beforehand, right? So these, on-demand servers, as they like to be marketed, are actually not truly on-demand as far as I'm concerned, right? They take ages to spin up. And so when you're thinking about horizontally scaling your applications and you get that spiky load in, say, a little 5-minute time window, and you think, oh, don't worry, we'll just push the magic AWS button. Well, it might actually take an hour for those AWS boxes to come up, and by then it's already too late. So what the cloud promises you is you have to check very carefully. And again, it actually boils down to reading some hardware manuals, talking to some system administrators and some DevOps people, and finding out what the real numbers of these systems are. Oh dear, my phone's died. Can no longer control from phone. Maybe I can? Yes. Excellent. Cool. You cannot virtualize into more hardware. I would say a good 25 to 30% of my customers don't know how to count. They do things like, we have 16 gig of physical RAM on the machine, and so we will allocate 32 gigs worth of virtual operating systems on that machine. Can anyone tell me how many 32s fit into 16? It's not very good. But if you actually check yourselves how your applications are deployed, I would double check with your system administrators and the people who run your infrastructure as to whether they can count, and you may be unpleasantly surprised. And what will tend to happen is that these virtual operating systems, in particular these virtual machines, are actually very good at time sharing and very good at sort of swapping the resources between each other, but all sorts of nasty things can start to happen, especially under load, right? One of your VMs all of a sudden may just be completely restricted with any CPU or RAM that it actually wants. Quite often, lots of nasty paging from the hard disk will occur, so on and so forth. So just because you have these dynamic virtual environments you can sort of spin up and start up and distribute across actual physical hardware, you have to count the numbers, which is again why you have to go back to your hardware manuals and understand what you're running on. So, number one tactic that you take away. So for the 90% of you who said you don't know what physical hardware you run on, go and find out. Get it printed out, A4 piece of paper, whack it up next to your monitor. Always, always remember what it is. And find out when it changes as well, right? What is performance tuning? Lots of different people have lots of different ideas what performance tuning is. We sort of have an idea that it's 4 or 5 broad categories. It's understanding of the actual underlying technology, right? This is the fun, cool bit. You get to learn about Docker, get to learn about NUMA architectures. You get to do some deep technical dive into fun stuff. You know, how do CPUs really work? Level 2, level 3 caches, all that good stuff. How does the JVM work? How do garbage collectors work? How does the just-in-time compiler work? How does thread stealing work? All this sort of good stuff. There is a methodology you can use. We have a methodology which we came up with ourselves over 20 years of doing this stuff as human consultants. We call it the Performance Diagnostic Model, and I will show you some diagrams, a sort of a flow chart of how you can follow this model yourself. But performance tuning is actually a science, right? Most people think performance tuning is sacrifice a chicken on the altar, light some black candles, go to Stack Overflow, change some minus random setting on your Java runtime, rerun the test and pray. Right? It's actually a very scientific process you can go through, and it's really boring. So one thing I'm going to warn you about as well, if you think that performance tuning is cool and fun and sexy, it is not. It is dull. Because you run one tiny experiment, you measure the results, you change one thing and one thing only, and you run it again. Some performance tuning exercises we've been doing have now been running for more than 18 months for certain customers. Just to give you an idea. You need to understand your architecture. Are you on cloud? Are you in a data center? Where is that data center? Who knows where their data center is? Yay, oh, that's better. So you know where your data center is, you just don't know where the hardware is that's sitting in it. Okay, it's a start. Diagrams. For those of you here who call yourself solutions or enterprise architects, do I have any of those in the room? Well, there's still a couple. We thought it had died in the 90s, but you're still here. Actually, enterprise architects are still surprisingly good at this. They get out Microsoft Visio, and they're very good at drawing the lines between all the boxes. And that's exactly what you want to do. You don't have to use formal UML or any formal techniques. Get with your colleagues around a whiteboard, get out your drawing skills from when you were a toddler, and start drawing out where the boxes are physically and also logically what the software flows are doing. Okay? Are there remote calls between a service and a database, so on and so forth. It's important to understand the real performance requirements. If you don't know what target you're tuning for, it's completely pointless tuning. Tuning just to go fast is not good enough. You want to have things like, we want the login pages to always respond within 1 second between the working hours of 9 and 5. After 5 o'clock, we don't mind if there's some degradation. And if you really push us, it's actually okay if this is only true 99.999% of all transactions that come through to the system. Right? That's the kind of statistical requirements gathering you want to push your users into. And quite often you're going to have to use non-technical language to get them there, but you can use hedge words like, okay, so for a vast majority of the time, you need this to be back in 1 second, but if every once in a while it's 3 seconds, that's actually kind of okay. And you yourself can convert that into sort of some statistical curves. You need to understand a little bit of math. Usually high school or first year university statistics is good enough. I sucked at math. This is why I'm the CEO, and I hire people smarter than me to do the math. You want some tooling. You want load tests, right? So unless you're really, really pro and you've got a load balancer in front of your production data streams and you're splitting off your production data streams A, B into your test systems, highly recommend this, by the way, if you can set up that infrastructure. You need to have some sort of load testing tool, whether that be Apache JMeter, Gatling, using BlazeMeter, which is a software as a service version of that, so on and so forth. You'll need to get some metrics and some monitoring out of your system. If you're not measuring, then you can't make any decisions. My company is jClarity, so I'm going to tell you to buy our stuff. but I will actually tell you about some free tools along the way. And you want a performance testing plan. If you remember earlier, I said it's a scientific process. You don't just wake up one morning, grab the team together and say, hey, we're going to do some tuning this morning. You need to have a dedicated plan. What are the use cases we're testing? What's the load test we're doing? Are we doing spike load tests? Are we doing endurance tests? Are we actually doing underutilization tests? So on and so forth. And I am 15 minutes in. Okay, cool. Performance tuning is fundamentally about this. It's about removing bottlenecks. And a bottleneck is basically where a system is oversubscribed, right? You're trying to create too many objects on the heap, and Java can't keep up, or you don't actually have enough physical RAM for Java to keep up. Okay? You have asked your system to split this task into 1,000 concurrent threads, but your CPU only has 4 cores. Going to be a problem. That sort of thing. So tactic number 2, the other takeaway you want to have, right? Know where your hardware is, know what the specifications are, and know what your actual system architecture looks like. Where are the data flows going to? Where are they coming back from? Next key thing, timeboxing. I'm going to run a little bit of experiment here. Humans suck at measuring time. We are absolutely terrible at it. And I'm going to prove this to you. I want everybody to close their eyes and count to 10 seconds and then raise their hand when they think they got to 10. On my mark of 3. So 1, 2, 3, go. Wow, okay. About 80% of you have had way too much coffee this morning. So on average, people were putting up their hands at about 7 or 8 seconds. So that is a huge inaccuracy, huge. But this inaccuracy can also be used to your advantage. Humans can't actually perceive small percentage gains in performance improvements. So you don't actually ever want to or need to spend time improving your end-user response times by, say, a difference of 4 or 5 percentage points, as it were, because humans won't detect that. Okay. Other end systems might, so if you're trying to improve performance of a system-to-system piece of componentry, then you can start eking out these types of gains. But when it comes to humans, you typically need to have a gain of more than 15% for them to actually notice it. Fun fact. You want to build a response time budget. And here's a very simple traditional client-server architecture with a database at the back end. You want to have a point which measures time in and time out at each of the dots that you see there on the diagram. And what you're basically trying to identify is what part of my architecture is a slowdown in. It's pretty simple. But unless you've got these measurements in place, you don't know whether the fact that the website didn't respond in 10 seconds was due to the client, was a JavaScript app slow, the network, did someone cut a cable, the app server, the data store, third-party web service not responding, so on and so forth. If you're using a fancy microservices peer-to-peer style architecture, good luck. It's actually really, really hard to build a time response budget for these things. There is a new standard out called OpenTracing, opentracing.io. I highly recommend you take a look at it. It seems to me to be one of the reasonable efforts out there at the moment to try and sort of figure out how to do this stuff. Really, really difficult otherwise. Which another way of saying is don't do microservices, just stick to the old school way of doing things, much easier. You can even write your own simple timer API, but there are actually lots and lots of tools and libraries out there. You can just do a Google search. So, tactic number 3, make sure you have an actual measurement in and out of each point in your architecture. Otherwise, you're going to be completely lost. You'll never even find the haystack, let alone the needle in the haystack. Okay, going okay for time. And now on to the crux of the matter, the performance diagnostic model. This is what we use as human consultants to go in and very, very quickly performance tune systems. And it doesn't matter what the system is. We honestly don't care, right? It can be a Scala system. It can be a distributed system. We've diagnosed Twitter's core messaging system. We've diagnosed a client piece of Swing desktop application. We've done all sorts. We follow the same methodology every single time. Okay, so it always applies. And it actually applies to most managed runtimes. So if you're performance tuning Python, Ruby, .NET, Node, anything like that, you can actually follow a very similar methodology to find out what's going on. And here it is in a nutshell. Looks a little bit confusing, but the question you always ask yourself is, what the heck is my CPU doing? Right? Very simple. What is my CPU doing? If it's kernel busy, so if you look at the CPU statistics and you see it's doing lots of kernel activity, that basically means there's a piece of hardware doing an awful lot of work. All right? Lots of disk writing, lots of network writing, lots of paging of memory, lots of context switching perhaps, so the CPU is being fought over by several applications or several processes, so on and so forth. There's an extra step you need to go beyond here because you need to find out what piece of software is causing this hardware to do all of the work. Okay, but I'll go into that shortly. So that's sort of one area you need to look at. If the CPU alternatively is actually what we call user or application dominant, so it's basically mainly doing user activity, then in the Java world, either it's the JVM probably doing some poor garbage collecting, that's usually the most common cause, but there are other JVM things that might be going on, like biased and unbiased locking might be causing some horrible long-term safe pointing, all sorts of other stuff might be going on. Or it's your actual application code which is hot and it's just burning all of the CPU time. This is surprisingly rare. As Java developers, you tend to want to look at your source code and say, oh, it's that concatenation of string we're doing a million times which is causing our code to be slow and rubbish. Almost certainly not. And I'll actually show you a little bit later on how ridiculously good Java is at optimizing your code under the hood. It is stupidly good. So I would say out of all the issues we've seen, and we've tuned probably a couple of thousand systems by now, that user application issue only crops up about 3 to 4% of the time. It's almost never your hot code, unless you're working in a pretty specialized area. The JVM is quite common, especially around garbage collection today. And one of the most common ones today, especially in cloud environments, is the no dominator black box in the bottom left corner. If your CPU is doing pretty much nothing, and your users are complaining that your website is slow, well, why is your CPU doing nothing? Right? It's because your application is not able to do any work. Why is it not able to do any work? Maybe there's deadlocked threads inside your JVM. Maybe your database isn't responding. Maybe a third-party web service isn't responding, and your app is just sitting there waiting. Right? Those are kind of the three broad categories. So you just have a look at what the CPU is doing. Does everyone know the tool vmstat? Yeah? Who here runs on Linux in production? Excellent. Right. After today, go log into a Linux box, type in vmstat if you've never used it before, or go man space vmstat. That's the manual page for vmstat, tells you how to use it. And you basically just run vmstat, and it will tell you what your CPU is doing. There it is, on the right-hand side there. That's what your CPU is doing. Can anyone tell me what this CPU is currently doing? Is it kernel dominant, user dominant, or is it doing nothing? It's doing nothing. Right, the idle column there is in the high 90% of the time. So this system is, as far as the CPU is concerned, pretty much doing nothing. So I instantly know that if my users are complaining that the application is slow on this box, it's not garbage collection, it's not hot code, it's not poor disk activity. I can eliminate all those things. Now I'm starting to look at things like thread pools, database connections, that sort of thing. Okay, so very, very quickly you can eliminate a whole class of categories of performance problems, and you can start diving into what the problem really is. So always remember, what is your CPU doing? 3 o'clock in the morning, when you're tired, you have your coffee or your can of Red Bull, you look up at your monitor and you've got the piece of paper next to the monitor which just asks you, what is your CPU doing? That's what I have at home. It's saved me many, many, many times. So going back to the top left-hand box where I talked about kernel activity being dominant, there are a whole bunch of reasons why the CPU might be kernel dominant. There might be context switching going on. So this is what happens when an Oracle database wants all the CPU and your Java app wants all the CPU. There's not enough CPU to go around, and they both just start fighting over it. And Linux does the best it can to go, yes, Oracle, you have a little bit. No, Java, you have a little bit, and so on and so forth. Sometimes it's just Java itself, right? Java, if you haven't coded your threading inside your Java application properly, it itself starts fighting for CPU cores and CPU time. Never a good look. Tools like VMstat and IOstat will very quickly tell you if it's disk writing or disk reading or some sort of hard disk activity which is going on. Especially if you're still running old spinning Rust or spinning ceramic drives, as we call them, so non-SSD drives. Remember, go back right to the start of the talk. What actually is your physical hardware? Do you have SSD drives or not? Do you know? Find this out. There are virtualization tools, KVM tools, VirSH, whole bunch of monitoring tools around Docker with Kubernetes, etc. And if you want to find out if you're destroying your network, netstat, again, free tool on the command line. Wireshark, also a fantastic tool, also brilliant for spying on your neighbors' Wi-Fi networks to see what they look at. So Linux tools, command line tools, are the cheapest, fastest ways to very quickly figure out what's going on. So learn how to use them. If you don't know how to use them, go talk to your local system administrator. It's actually the best way to start bridging that gap, because I know most system administrators hate developers and most developers tolerate system administrators. The DevOps movement was supposed to bring the two together, but I think there's still a major cultural split there. But this is one of those sort of little peace overtures you can make. Just be humble and say, I'd really like to understand how to monitor these performance issues as the Linux operating system sees it. And in return, oh Mr. or Ms. System Administrator, I will tell you how the black box of Java works with garbage collection, etc. And they'll love you for it, because they hate Java. Java is this horrible big black box they can't get into. They really don't like it. If the CPU is moving towards user activity, the first thing you want to do to quickly eliminate a class of problem is look at the garbage collection log. Garbage collection used to be almost this wonderful free thing that Java gave you, which never really used to impact your system. And that's because there was just this sweet spot that hardware was so powerful, and the types of applications we were building in the early 2000s just never troubled it. The problem now is we're either trying to run applications in really small heaps because we're doing microservices, Spring Boot, Docker containers, tiny Java heaps, or we work at big banks and places with huge data caches. So we're running 100 gig heaps or 256 gig heaps we've even seen out there in the wild. And the garbage collection algorithms that are currently out there today just simply can't cope. New ones are being designed, new ones are coming in, so G1's coming in from Oracle, Shenandoah from Red Hat, so on and so forth, to try and help out. But what tends to happen is that the JVM either has to stop the world to try and clean up an absolutely huge chunk of your heap, or it spends a massive amount of time trying to do cleanup while still giving you a little bit of CPU so your application can continue, which is what we call throughput. Either way, it tends to dominate the production problems we see in terms of performance. Those are the three flags you always want to switch on in production, unless you are in the low latency trading space, and if you are, then you probably shouldn't be in this talk anyway. Less than 1% impact on your running production JVM to switch this on. All right? And it gives you the GC log you need to find out whether it's a GC problem or not. Use a GC log analyzer to find the problems. We obviously have a paid-for tool. There is also a free tool called GC Viewer, if you don't have any budget or if you know your manager will never pay for anything. Here's a sort of example of the type of analysis that a GC log analyzer can do for you. GC Viewer, by the way, will show you this exact same view, so I'm only using my tool just because it puts out a slightly prettier graph. You can see that along the bottom on the right-hand side there, this Java heap is doing a full GC every split second continuously. And it is recovering just enough that it goes, yep, this heap is still alive, so I'm not going to out of memory error, but I do have to full GC again straight away. And a full GC stops your JVM. None of your application threads can continue running. So as far as the end user is concerned, this application has just stopped dead. Right? As far as the CPU is concerned, you would see the CPU user activity start spiking. You take a look at the GC log and you go, aha. In this particular case, the heap is just undersized. Right? We'll just double the size of the heap, rerun the application, see what happens next. Pretty simple. Here's a fun one. This is what a memory leak looks like from a garbage collection log perspective. Again, you look along the bottom of the graph. That is the size of the heap after a garbage collection has occurred. The red ones are the full GCs, the red diamonds and the red crosses. So basically, that is stopping your entire application, cleaning up everything it can, and then off it goes again. As you can see, over time, as this application keeps trying to clean up after itself, more and more gets left behind. In about 2 weeks' time, this very, very important trading system is going to blow up with an out-of-memory error. Okay, so again, you would see increasing CPU activity take place as more and more full system GCs occur over time. This is what a healthy application looks like. If you see this type of log, give yourself the thumbs up. You've clearly done a good job. People like to then know how to find memory leaks. There is a free tool called Visual VM with Java 8 and earlier, I believe. You can actually just find it in the bin directory of your JDK, or you can download it. Just search for Visual VM. It's a memory profiler, it's a CPU profiler, it's a basic profiler for everything Java. It's got its drawbacks, it's got its flaws, but it generally is good enough to do this. And what you basically want to do is find the code which is generating all of the objects continuously and not cleaning up after itself. And what you do is you just attach Visual VM or the NetBeans profiler, you attach it to your running JVM, you hit the magic memory profile button, you profile for a good length of time. Okay, you need to do this for a good length of time. And if you've turned on the magic record my stack allocation traces, my allocation stack traces, sorry, you will then get a view like this. So basically, concurrent hash map hash entry is the dominant thing that is being created in this heap. Okay, this is a thing that is constantly being created. You see the generations count on the right-hand side, which means it's been alive for continuous generations. It's effectively not being cleaned up after itself. So new ones are always being created. And then all we have to do is just walk down the stack trace until we get to the line of code which does not look like a Java class. Because Java, I dare say, almost has no memory leaks left in it, right? The Java JDK team are very, very good at not having memory leaks inside Java itself. You see there's an application there called Hawkshaw. Aha, that's the application source code which is creating the memory leak. So you go into your source code and you find out what the memory leak is. That's simple. And after this, I'm happy to show anyone live how to go about doing that. So don't be afraid of getting out the memory profiler. That's my piece of marketing. But quite seriously, Visual VM or Eclipse's MAT or NetBeans' profiler, I can't remember if IntelliJ comes with a decent one or not, but yeah, they're all good. How am I going for time? Need to go a little bit quicker. Okay. So if you've eliminated garbage collection, right, so you got that lovely blue line, spiky, sawtooth pattern, but it was the fact that your CPU still had lots of user time, then you need to actually look at your application code. All right, and this is all about CPU or execution profiling. Now, as I said before, Java is stupidly good at optimizing your code. Here is a tiny amount of the optimizations that the hotspot C1 and C2 compilers run for you. This is just a small amount. I can't remember how many there are, but there are hundreds. They are so complicated, and the interactions between them are so complicated, that nobody actually understands how they all work anymore. This is one of the reasons why possibly Hotspot will be replaced in Java, maybe 10 or 11 or 12, with this new technology called Graal, which is similar compiler technology, but can be reasoned about and has a Java interface, which is a lot nicer. But despite that, most people would argue that Java's hotspot profiling and dead code elimination and other techniques is the best out of all the managed runtimes out there today. That's why Java is so good. Method inlining is the killer feature of this. So if you have class A and you're calling a getter or a setter in class B, and it gets called often enough, the JIT will just go grab that code in class B and it'll suck it into class A and effectively get rid of that code in class B. And then all of a sudden it's got this new, slightly larger chunk of code that it can perform extra special clever analysis over. It can figure out things like, will that if statement ever be called? Or can I optimize that loop? Because I always know that the true path is going to happen. Stuff like this. 35 byte codes or less is what you need to have one of your methods actually be optimized by the just-in-time compiler as a rule of thumb. So when you're writing your source code and you compile that source code down, you can actually have a look at the class file and you can use a tool called JavaP. Again, this comes free in the bin directory of Java itself. You just go JavaP -c, name of your class file, and it will tell you how many byte codes each of your methods are. And if your methods are 35 byte codes or less, then they can be candidates for being optimized by the just-in-time compiler. So if you've got particular important business methods that you need to go really, really fast, you need to make sure that they're 35 byte codes or less. Some more in-depth detail about how all that works, which I'm just going to skip. So here's an example. Who here has done FizzFuzz or FizzBuzz? Interview question. Yes, it's still a firm favorite. So this is a typical Java enterprisey, very verbose source code, but extremely readable way of doing this. I would expect, a junior to mid-level Java developer I was interviewing to come up with a solution like this. So, we have 2 good slides here worth of source code just to do FizzFuzz. All right? So we get the numbers, we process them, we figure out the range, we figure out what the division should be, we do some printing, so on and so forth. All of the source code, JIT turns into that. Right? Which is perhaps how a C developer would have written this in the first place, admittedly, in terms of how the source code is written. But it's amazing the amount of dead code elimination, inlining, a whole bunch of these other clever techniques, constant propagation, all sorts of other stuff that goes on. So I guess what I'm trying to tell you is when you're writing your source code, don't optimize your source code. Write your source code for readability and maintainability. If you really care about optimizing it, just make sure it's 35 byte codes or less, and then the JIT will take care of everything else for you. Unless you have several PhDs in computer science and compiler theory, trust me, the JIT is smarter than you are. Okay? Here's another example of how the JIT works. Can anyone tell me how long it takes, for example, to create, let's say, 10 million objects in Java? Yeah, a few people have figured this out. 0. So this is a bit of code I love showing all of my Node.js and Ruby friends, telling them how fast Java is. We can create 10 million objects in 0 seconds. Because what happens here is that object O never escapes that loop. Right? It's never used outside. It's never referenced outside. So the just-in-time compiler says, well, if it's never used outside, it's never used inside the loop, I'm just going to kill it completely. Just removes it. Dead code elimination. And so that for loop actually executes nothing. So it returns in 0 seconds. This is why micro-benchmarking in Java is hard. Again, you can use a free tool, NetBeans Profiler or Visual VM Profiler. Instead of hitting the magic memory profiling button, you just hit the magic CPU profiling button. Big red bar is bad. The big red bar is a bit of your Java code which is causing the CPU to do all the work. And again, if you have pushed the magic record my allocation stack trace button, you go down all the Java classes, because you'll see lots of things like, char array, string, lots of Java primitives at the top of the stack trace, until you finally get to your piece of code and you go, aha, it's that ridiculous call to hibernate I made, which is killing the CPU. Not uncommon. If you really have to go tuning your source code, then there is a free tool under the Adopt OpenJDK organization on GitHub called JITWatch. JITWatch has this beautiful 3-panel system. Your Java source code, the Java bytecode it produces, and then the actual JITted machine code that produces. So you can take your methods and go, ooh, if I just tweak this little bit of code, oh, now I'm under 35 bytecodes, fantastic. And the machine code that gets thrown out is, well, I can't read it, but if I could, I will impress all my friends with how I can read machine code. But this is actually the very tool that even the Oracle engineers now use themselves from time to time to figure out what the heck's going on internally. A guy called Chris Newland here from the London Java user group is pretty much the primary author. It's a fantastic piece of software. Also, if you are going to micro-benchmark, please use the tool called JMH. It was written by Alexei Shipalev, who was formerly the head of performance for all things Java at Oracle and is now head of the Java performance team at Red Hat. He has done lots and lots of work to do things like make sure that when you're running a micro-benchmark, switch off the garbage collector, because that's going to interfere your measurement, this sort of thing. So if you need to do micro-benchmarking, then use JMH. So, if you must optimize for JIT, use JMH and JITwatch. It will tell you what's going on. And you can use Java P-C if you can't be bothered using those tools, and if you want to show off to your friends a little bit about how you look at the bytecode of a class file, 35 bytecodes or less. Don't forget it. I'm definitely running out of time, so I'm going to go very fast now. So we've covered the user space stuff. Is it garbage collection or not? If it isn't, then it's application code. You can use JITwatch and things like that. If it's kernel, use all the Linux command line tools to find out what's going on. If it's idle, then something's waiting or deadlocked. It's all to do with basically there are no threads or processes coming into the CPU. Boring. So there's lots of different ways you can do serialization and inter-process communication, and you know about them all. Everybody now just uses REST and JSON, right? Is anyone not doing REST and JSON? Anyone here still doing JMS? One person, one unhappy person. Never mind. We can skip that. Again, Wireshark is a very, very useful tool to find out about things going in and out of your network. If you've made a database call and it's not coming back, or if you've made a third-party web service call and it's not coming back, Wireshark will actually sit literally on the wire and tell you, and it'll have a look at the packets, you can filter them, all that good stuff. If it's a problem inside the JVM and there's things like deadlock threads or live lock threads, or there's the threads are fighting for each other, there is this very simple thread state diagram you can follow to figure out what's going on. Most people don't bother. Most people just use a tool. Again, NetBeans or Visual VM comes with effectively a thread analysis tool. You just hit the magic "What are my threads currently doing" button, and it will look at all your threads. You'll see here, this is a typical HTTP thread pool, probably coming out of Tomcat, I think. And you can see here, for like a lot of time, those threads are actually waiting. And then there's a burst of activity, the green in the middle, and then they're off waiting again. So if you see that all of your HTTP thread pools, for example, are yellow, they're waiting for something to come in, and your users are saying, your web app is slow. Well, you're like, okay, so somebody broke the Apache web server in front of my Java server, and no data is coming into my Java server. That's why all these threads are waiting. Right? Those are the types of conclusions you can make. Or, I'm getting Google ads coming in from the third-party web service, and I'm waiting for them to come in. Anything along those lines. You can also find out whether your threads have been stopped or locked. As you can imagine, the red bar is bad. If you're colorblind, I apologize. I don't know if you can change the colors in NetBeans, actually. There are other tools that do cater for colorblind people. NetBeans also helpfully comes with its own Deadlock Detector. Again, this is a free tool. Visual VM does the same thing. It will tell you if thread 1 is locked on thread 2. Here is the big caveat. No profiler is accurate, okay, especially in Java. Right? For profilers to do profiling in Java, they have to do things like ask threads to stop so they can go get the information. They have to do sampling. So quite often, they can either miss the problem, or they can miscount the problem, or if you're not profiling over a wide enough time window, or you're not sampling quickly enough or slowly enough, you're going to get the wrong information. And a fun trick you can do to show your friends that this is the truth is you generate some performance problem. Maybe you deliberately deadlock a couple of threads or something along those lines. Then fire every single common profiling tool at it, and they'll all give you a slightly different answer. This is where the mathematics comes into it and the scientific rigor. You need to make sure that when you're doing profiling, you're profiling over a set time window, the same time window every single time, that you're doing your sampling rates the same every single time, that you're making sure you're taking enough measurements that so when the profiling and the sampling misses certain data points, you're still getting the right curvatures. Right? There are some really cool profiling tools that are starting to come in. Things like the honest profiler, the async profiler, which actually work under the hood of Java. They're kind of looking at what the native threads are doing. The great thing about them is that they're more accurate. The bad thing about them is that they're native agents, and if they crash, your JVM crashes. Some customers don't like that, apparently. So as a summary, you need to know what your resources are. Go and find out what all of your hardware is sitting on and where it is sitting. Do the time boxing, draw your architecture diagram, and make sure you're getting numbers in and out of each component. You can follow that performance diagnostic model. What is your CPU doing? Is it going towards kernel? Is it going towards user? Or is it doing nothing? If it's system or kernel, use Linux command line tools. Is it rampaging in and out? Is it disk activity? Is it context switching? So on and so forth. If it's in the user space, garbage collection log first. Within 30 seconds, you'll know whether it's garbage collection or not. Otherwise, you have to go into the more difficult execution profiling. And if it's idle or wait, then get out the threads profiler and see if you can find out whether it's your database pool that's waiting, your thread pool, your HTTP pool that's waiting, or if you've got a deadlock situation. This is some of the stuff we're doing to help. So we work on OpenJDK directly. If you want to find out more, just see me afterwards. We've used machine learning to try and do this stuff quickly for you. And I think I've probably run out of time for questions, so you will have to just find me off to the side so there's enough time left for the next speaker. No, apparently I have 4 minutes left. 4 minutes of questions. Yes? So how do you get requirements? Okay, that's a very good question. How do you get requirements of users without them picking out random numbers out of the air? So you can actually go back and show them some well-known user studies that companies like eBay and Amazon have done and some of the large gambling and e-commerce sites. So for example, most users will just say a website is fast if everything responds in 1 second. Most users will notice a delay, but will still stay on the website if it's 3 seconds or less. If it's more than 3 seconds, they get bored and they leave. So you can start using those kind of user studies to help guide your users into giving you the numbers that are actually truly important. Right, so are their end users an e-commerce site, or are they internal users? And if the internal users are locked to your application, then hey, even if the thing pauses for 10 seconds, they can only use that HR application, right, to fill in their timesheets. Tough luck. So it's maybe not so important. Yes.
First, thank you for the presentation.
No problem.
Cheers. You mentioned that firing instances or containers on the fly in production or on the cloud takes a lot of time. Yeah. So can you highlight briefly what could be the reasons? The
reasons for
taking that long. You said that firing instances on the fly when you were
I see. Right. So
it was taking a long time. What are briefly the reasons behind this?
It's all about how busy a particular data center is, in particular for Amazon or Google Cloud or Microsoft Azure, right? So everyone thinks there's a sort of infinite cloud of machines out there. Well, it's actually not the case, right? So if Amazon West Coast is having a busy day and there's actually only 5 physical machines left that can spin up virtual machines on that physical machine, then you're going to have a bad time if you've asked for 30 virtual machines, right? Because you have to wait until some other resources actually come free. So Amazon and companies like that don't actually have limitless hardware, and that's typically what happens. And they actually allow customers to pay for priority as well. And typically for people like you and I, we don't have the budget to get priority at Amazon. And if Netflix wants an extra 3,000 servers, they get it first. Yeah, Amazon are brilliant at billing, by the way. So, if you really want those machines, they're always happy to give you that priority if you're willing to pay a lot of money. 2 minutes left. Any more questions? Everyone's now reading their hardware manuals. Yes, there's one over here. That is a fantastic question. What impact does profiling have on the application? I actually forgot to mention this, so bad, naughty me. Profiling all of the traditional Java profilers, so Visual VM, New Relic, App Dynamics, even our tooling, we try very hard not to do this, they all impact applications quite a lot. You can see up to a 20% impact in terms of throughput can actually occur, depending on how busy your application is. What our tooling does is we only actually jump in and profile when we know there is already a problem. And so we kind of work with our customers and we say, well, your app was already dying. If we add an extra 10% overhead to that for 2 minutes while we figure out what's going on, maybe that's not so bad. But if you've got a profiler which is continuously profiling, and I think some of the tools do this, like New Relic does this, we have a mode where you can do this, you will be adding that overhead all of the time. Absolutely. So yeah, you do have to pay that price. There is one tool which is probably the most lightweight. It's Oracle's Flight Recorder. They've got lots of hooks internally into the JVM. It's a fantastic tool. If you can afford Oracle, I would go for it. But affording Oracle, well, they're reassuringly expensive. And now I'm out of time, so thank you very much for listening. I hope you have a great rest of your day.